Who recovers from childbirth faster? A randomly selected sample of 16 insured women spent an average of 2.4 days in the hospital for a routine childbirth with a standard deviation of 0.62 days. Another randomly selected sample of 16 uninsured women spent an average of 1.8 days in the hospital for a routine childbirth with a standard deviation of 0.53 days. Find the 98% confidence interval for the true mean difference. So let's start there, right there. It says find a 98% confidence interval for the true mean difference, right, between the amount of time spent in the hospital after childbirth for insured women versus uninsured women, right? So we're going to start with looking at the data here. So there's a sample of 16 insured women, right? They had a mean of 2.4 days, standard deviation of 0.62 days. Another group of 16 uninsured women spent an average of 1.8 days in the hospital for a routine childbirth with a standard deviation of 0.53 days, right? And then finally, you see down here at the end, it says assume equal variances. So when they tell us assume equal variances, we're thinking that it's probably a t-test because that's where that becomes important, or t-interval, sorry. And then we look over here and we see that the sample sizes are, yes, small, so it's going to be a t-interval we're working with. All right, so let's start with the very first part of the problem, which is to talk about the data, right? So let's organize the data and put it into a nice summary set of notation here. So let's start with the first thing we're going to list is the insured women. So we'll do INS for insured, and then we'll do uninsured, right? INS. Okay, so just an abbreviation. We could even use just I and U if you want. But either way, we have N equals, X bar equals, S equals for each group, N, X bar, and S. All right, for the N for the first group is 16. They had a mean of 2.4 days and a standard deviation of 0.62 days. Then for the next group, it's 16 again. The X bar is 1.8 days, and then the standard deviation is 0.53 days. Okay, now at that point, we're going to write down the confidence level is 0.98, which leads to the idea that alpha is 0.02. Now, our next step in a confidence interval after listing all the data is to go ahead and find the t critical value, in this case t because the small sample sizes, right? So t alpha divided by 2 with degrees of freedom n1 plus n2 minus 2. So n1 plus n2 minus 2 can be calculated pretty easily here. And then alpha divided by 2, that's going to be 0.02 divided by 2, so it'll be 0.01. And then n1 plus n2 minus 2, in that case, we're going to basically have 32 minus 2, so we'll get 30. All right, so this is the alpha we have to look up on our table. So we're going to look up 0.01, look at that column. We're going to go down to 30 degrees of freedom to get our critical t value. So let's go to the table now and see what that gives us. Okay, so we're looking up 0.01 with 30 degrees of freedom. So we're going to be at the 0.01, area in one tail 0.01, and go down to 30 degrees of freedom. Okay, so let's see what that gives us here. So 0.01, 30 degrees of freedom is 2.457. Okay, so we found our critical t value to be 2.457. Now we have that critical t value, the next step is to take that and plug it into our margin of error formula. So our margin of error formula is going to be t alpha divided by 2, the square root of sp squared over n1 plus sp squared over n2. So remember, these are our pooled estimators of the standard error for x bar 1 minus x bar 2, and that's essentially going to be a weighted average between the given sample variances that we have. So let's take that and work that out separately. So sp squared is equal to, and now we're going to plug in n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared, s2 squared. And then it'll be n1 plus n2 minus 2 at the bottom. Now, the n1 minus 1 is going to be 15 times the standard deviation, 0.62 squared, plus 15 times the standard deviation of 0.53 squared. Okay, so again, we're going to have the top part like that, and the bottom part, of course, is going to be 30. So that's n1 minus 1 plus n2 minus 1, basically. All right, so let's work that out and see what we get. So we're going to plug that into our calculators. So we're going to do 15 times 0.62 squared plus 15 times 0.53 squared. And when we're done with that, we're going to divide that by 30. All right, when you get the answer, you're going to get 0.33265. 0.33265. So that's our pooled estimator, right? There it is. So the sample variance, the pooled sample variance for the problem here for our estimator, x bar 1 minus x bar 2. So we have that number. Let's take that, plug it back into our margin of error formula to get the solution for that term. All right, so the margin of error is going to be our table value, 2.457 times the square root of 0.33265 divided by 16 plus 0.33265 divided by 16. Of course, you could have just said 2 times that fraction since they do have the same denominators here. All right, now let's take that and plug it into our calculator. So we end up having for our first number 2.457 times the square root of 0.33265 divided by 16 plus 0.33265 divided by 16. All right, plug that in, we end up with 0.50101 dot dot dot, right? So 0.50101 and then just on and on and on. I'm going to store that in our calculators. So I'll store it as x, and I can come back and use that in a moment when I finish the problem. All right, to finish the problem, remember you just do that simple addition and subtraction problem that involves subtracting and adding the error to our estimator x bar 1 minus x bar 2. So let's go ahead and work that out now. So I'll lay this on top of the other one. And let's see what we get. So the relevant information from before was that we had the insured group and the uninsured group. And for that group, we had the x bar being 2.4 and the x bar for this group being 1.8. Okay, so what we have to do then is to fill in the following interval. We have to do x bar 1 minus x bar 2 minus the error, then x bar 1 minus x bar 2 plus the error. Okay, so the difference here is going to be 2.4 minus 1.8, right? Minus the error, comma, 2.4 minus 1.8 plus the error. All right, so now the next step to the problem is to go ahead and do this subtraction. You're going to need an answer, of course, of 0.6, so 0.6 minus the error, and then 0.6 plus the error. And I'd put that error into our calculator, so we can just do that now as 0.6 minus x, and then 0.6 plus x. And when we do that, we get the following result. We get 0.099, let's say, and then 1.101. Okay, so both of these terms are positive, so the interval is completely positive. And what that means, since we did the subtraction in this fashion, we did insured minus the uninsured, it means that the insured group spent a significantly longer time in the hospital than the uninsured group did. And that could be because maybe the doctors are pushing the uninsured group out faster, or maybe they're leaving faster because they know that it's going to be very expensive for them. Whereas the insured group is either encouraged to stay longer or they are willing to stay longer because of the fact that they know that their visit is going to be covered under insurance. But either way, the fact that both of these are positive, it indicates that this group was higher. Because remember, when you do the subtraction this way, if the bigger one was the first value, you would get a positive difference. And since the whole interval is positive, we say that yes, there is a significant difference. So that's it. So essentially, I don't know what consequences this has for the healthcare industry, but if you look at consequences for a shorter hospital stay and they seem to be negative, then we might have some argument for either changing the policies towards uninsured people or trying to get more people on the insurance rolls.